Hi folks, my name is Tom Crawford. I work here at Technodyne Corporation. One of the things that we've done over the last 30 to 40 years is provide optical property training seminars for folks in the pulp and paper industry and those associated with that. And in these, we are basically spend a day going into their facilities or bringing a group of people together at a hotel, and we'll spend the day talking about the technical aspects of things like what is brightness and opacity and fluorescence and whiteness and gloss and color and so on. And our goal being to give the folks that attend a little better knowledge of what it is when they make a measurement. Where did that measurement come from? What is the relevance of that data, and how does it affect my operations? So you may be familiar with the yellow book that we've had in the marketplace for many years now. And in this book, we take those topics and we break them down into very manageable small sections so that you can sit and you can read that and get a better understanding. We're going to do the same thing with these videos. And so what we're going to do is we're going to take a topic, let's just say something like brightness. And we'll break that down into multiple small little tutorial videos, 10 to 15 minutes in length. And we'll just take that topic and we'll say brightness. What is the history of the measure? Where did it come from and why do we use it? Then we'll talk about the standards that are written around that define, say, a TAPI brightness or an ISO brightness. Then we'll talk about the calibration of that and how we use that measurement in the marketplace. So that if you've got 10 minutes, you can sit down and you can watch a section and learn something about that topic. And then if you've got a bit more time, you can sit and watch 3 or 4 of the videos, try and tie all that information together. So we hope that you enjoy these videos. We hope that they will bring some knowledge to your workforce so that as they make those measurements, they're doing more than just making a measurement. They're actually understanding what it is that they're measuring when they do that. So thanks for watching. Hi folks, and welcome to our tutorial series on brightness. Technodyne started back in the mid-1970s, and from the start we've always had a product that measured this property called brightness. At the time it was a TAPI brightness instrument. Today we make both TAPI and ISO brightness. But if you look back over time and you look at the number of measurements that our instruments have made in the marketplace measuring a brightness number, it's well over 200 million measurements that our instruments have made in the worldwide paper industry on this property called brightness. So it is probably the most measured property that you'll find when you go into a paper mill. I've been involved in the paper industry and the color industry for almost 30 years now. And in that time, I've been in mills scattered around the world, in the U.S. obviously, in Canada, throughout South America, Asia, Europe. Everywhere I go, they measure this thing called brightness. So it seems to be this common thread throughout the process is that if you're going to make paper, if you're going to make pulp, you're going to measure brightness in that process. Well, why is that? Well, that's what we're hoping to explain through these next several videos. Today we're going to talk about, in this video, kind of the history of brightness, where it got started, what was the original concept behind that, and then how we can apply that towards what we're doing today. Then the next video we'll talk about, just drill into TAPI brightness and talk specifically about TAPI brightness. And then third video will be about ISO brightness. The fourth video will be about what is the difference and the similarities between TAPI and ISO brightness and how we use that in the marketplace today. Then the fifth video will be about how we calibrate when we say something has a brightness of 90. Well, what does that mean? What is that calibrated against? So we'll talk about those things as well and how we tie it all together at that point. So over the next little bit, these videos will be about 10 to 15 minutes, and you'll be able to sit down and watch those and kind of complete a whole video in that amount of time. And if you have a longer amount of time, you can sit and watch them all together and see how they kind of all tie together to create the story, this property that we call brightness. But when you think about brightness today, and you go into a paper mill and you want to determine, all right, what are we doing here and what do we measure? One of the things we're going to do is we're going to pulp the fiber up. And when we pulp the fiber up, it's going to be a dark brown, something in this area here, okay? So there might be some pulp fiber that, excuse me while I kind of wring that out there, that has a kind of a dark brown cast to it. And so we'll take that and we'll make a hand sheet out of that somehow. And then when we make that hand sheet, we'll put that on the instrument. and we'll measure that, and we'll get a brightness number from that. And depending upon where we are in that decolorization process of that fiber, it may be as low as 15 or 20, but it also may be, as you've moved through that bleaching process and now you've got a whiter pulp, less color in that, it may have a brightness of 70 or 80, or maybe pushing upwards to 90. Okay, so depending upon where you are in that bleaching process and that decolorization process, you'll have a different brightness number. Okay, if you are a precipitated calcium carbonate manufacturer, if you are a kaolin mine, if you are a titanium dioxide manufacturer, you certainly want to know what brightness is, because your product is used as a filler or as a coating for that finished paper. And so that very much so affects the optical characteristics, and the ultimate brightness, the eventual brightness you'll have on a finished product will be dependent upon, to some extent, your product. If you're a tissue manufacturer, you want to have the right optical characteristics of that, and every tissue manufacturer measures brightness. Certainly if you are making copy grade paper, so you're going to run it through your copier, or it's for an inkjet printer sitting on your desk, you want to make sure that you've got a good optical characteristic to that and the brightness is correct. If you're a book manufacturer, certainly when you turn page to page, you want those pages to look the same. And so you're going to measure the brightness of that. If you are a board manufacturer, think about the economy today and how that has changed over the last little bit with e-commerce going on. And now the first impression you get of a product is when it is delivered to your office or to your workplace or to your home. And now you've got this box, and this box typically is going to have something printed on it. And that box is going to have an optical characteristic that as they manufacture, as a producer of components that are going to be shipped out, I want to make sure when you get that it looks good. And the same way for all the other companies. So you want to make sure the optical characteristics are right, and one of those characteristics is the brightness of that. You walk into a office supply store or a paper supply store, and you go in and there'll be just these rows and stacks of reams of paper, and there'll be all sorts of different colors of reams and packaging with that. And if you look at that tape that's on the end of that ream of paper, you'll see some data. There may be grammage on there, but probably the one that has the biggest number is this thing they'll call brightness. And it will say 96, or it will be 92, or it'll be 87. And you'll see some dollars change as you move up and down that scale, along with some of the other properties. But brightness is a very important parameter that they're going to find that's going to add value to that product. And so today, when we go in places, we see whether they're measuring TAPI brightness or ISO brightness, they're measuring brightness on everything. Now, there are things, and we'll discuss it as we go through this video series, that, you know what, brightness isn't relevant for. And so these guys right here, these bright colored sheets, these saturated colored sheets, well, you'll see that the whole concept of brightness measurement has nothing to do with this. And so if we're making this, we don't want to measure brightness of this, because it won't make a visual optical sense. But yet, we go into mills and we see folks measuring brightness of deeply saturated papers, and it's not a irrelevant measurement for that. So we'll talk about that a little bit later. So today we measure brightness on a number of different things. So it's important for us to understand where this brightness measurement comes from. What was the original intent of that, and how was it designed? What was it designed for? And then maybe it makes a little bit more sense of how we apply it today. So to begin that discussion, we've got to go back in history a little bit, almost 100 years, back to the state of Wisconsin, which is in the United States. If you think of the United States and you think of the central portion of the United States, and then in the upper section, northern section of it, is a state called Wisconsin. It's located on the Great Lakes on Lake Michigan. And in the center of that state, there's this area called the Paper Valley. And the Paper Valley was the home of, and still is the home of, many paper manufacturers and pulp manufacturers because of the trees that were in that area. And so it became a large paper producing region in the United States. Well, there was a company up there that was a pulp mill, and they were struggling with getting consistency in the product that they were producing for their customers. Consistency in the optical characteristics. What did it look like? And what they found is that from shift to shift, from day to day, from early of the week to late in the week, to even within the beginning of a shift to the end of a shift, that how people evaluated this versus this vary depending upon their state of mind or many other different things. And so today you might produce this, the next day they might say, you know what, that's good enough, we'll go with that. So a great variation in how it appeared, and so they needed to come up with an analytical tool for evaluating this bleaching process that they were going through. So they were trying to go from this, which was an unbleached product, to somewhere over here, some level of whiteness or decolorization of that to where it met a customer specification. So this company went to the Institute of Paper Science and Technology, which was located in Appleton, Wisconsin at the time, and this is the early 1930s, okay? And so the Institute had some of the leading physicists in relationship to the optical characteristics of pulp and paper. So they sit down with them and they said, okay, here's our problem. We're not generating consistent pulp visually from day to day. Can you help us develop an analytical tool where we can come up with some way of taking this pulp, putting on that, measuring it, getting a data point from that and saying, okay, the customer spec is X and now I'm here. What do I need to do to get it to here? Then I can create a range around that to say, okay, if it's in this range, then the customer is going to be satisfied with it. All right, well, that's our task. And so what the Institute went and did is they asked them to provide them with a lot of samples that would identify the problem. So this is bad, this is good, this is kind of in between, this is what the customer wants, this is what the customer doesn't want. So they had this array of pulps and hand sheets that they could put together to do this evaluation. At the time, General Electric Company was making spectrophotometers, and the Institute had one of these spectrophotometers. And it's not like a spectrophotometer today that we have in one of our instruments, which is, you know, about that big and weighs less than a pound. But this actually was a device that needed a big bench, and it was roughly 6 foot by 4 foot and weighed close to a ton. So it was a massive piece of equipment. But with that, you could take a sample and you could put it on that instrument, and it would measure the spectral characteristics of this sample, basically saying what is its light distribution across the visible spectrum. Okay, so with the concept of the visible spectrum, we need to take a little bit of a break and make some definition. Okay, so now what we're going to talk about is really the electromagnetic spectrum, and that's a big word and it covers a big space. But think of radio waves and sound waves and microwaves and any sort of wave that's going on. A small portion of that electromagnetic spectrum is what we call visible light, and that's in the region of 400 nanometers to 700 nanometers. So 400 to 700 nanometers is the range of the electromagnetic spectrum that our eyes respond to. Okay, just for a point of reference, a nanometer is a billionth of a meter. So if you think of a meter, a billionth of that meter represents a nanometer, and the average human hair, of which I don't have much of these days, is about 100,000 nanometers in thickness. Okay, so when we're talking about the visible spectrum, it's 400 nanometers to 700 nanometers. So it's a very, very small region of that full spectrum. But again, it's what we respond to and what we call light. So just to make a real quick definition here. Okay, so we'll say 400 nanometers nm to 700 nanometers. Okay, so 400, 500, 600 nanometers, that's what we call visible light. All right, and then for our definition, for the world that we work in, we're going to draw a line there at 400 nanometers and say anything that is below 400 nanometers, we're going to call that UV or ultraviolet energy, and anything above 700 nanometers, we're going to call that IR or infrared. Okay, so for us, in the definitions of what we're going to be working through, especially in relationship to brightness and the optical characteristics of paper, 400 to 700 nanometers is the visible spectrum. Anything below 400 nanometers is going to be ultraviolet. Anything above 700 is going to be infrared. Okay, so that's the world in which we're talking about. Okay, so getting back to the instrument. GE had made this spectrophotometer. The Institute had one of those. They were able to put that on there and measure all these pulp handsheets and collect that spectral data. Okay, what they found when they did that, and they plotted it, they didn't have an Excel spreadsheet at the time, but they plotted that out longhand, all right, is that when you were looking at something like this, an unbleached product, it had a energy distribution that looked something like that. Okay, that's kind of a ballpark representation of it, but it had low energy here in the 400 region, more energy out here in the 500 and 600, and the highest amount of energy over as it moved out into this 700 nanometer region. Okay, so let's break that down a little bit further. So again, for the sake of our discussion, for our world in the pulp and paper industry, we're going to break the visible spectrum down into 3 sections. Okay, the first section is going to be from 400 to 700, 400 to 500 nanometers. That'll be this section. And we're going to call that the blue light energy. Okay, so energy from 400 to 500 we're going to call blue light. Okay, then we're going to break down the next section, which is 500 to 600. And we're going to call that the green light, green energy section of the spectrum. And the last piece, this guy right here, from 600 to 700, we're going to call that the red region of the spectrum. So we take the spectrum, we break it down into 3 macros, if you will. 400 to 500 is going to be the blue region of the spectrum. 500 to 600 is going to be the green region of the spectrum. And 600 to 700 will be the red region of the spectrum. Okay? So then, as we start to think of these pulp handseeds that they were looking at and measuring, we can see that this first hand sheet, which was an unbleached product, had little blue energy, had more green, and had most red energy. Okay, so when you have that combination of light energy, and when you watch the video on color, this will become a little bit more clear to you. But when you have red and green energy combined together with the absence or a little bit of blue, you get things that are in the yellow and the brown region of the spectrum, which is what we have here. So we see very little blue reflectance in this sheet because that blue is being absorbed by the sheet. So as you step through that bleaching process, that decolorization process, pulling this colorant out, what they found is that that was a lighter sample. This one was even lighter. This one was lighter. And just continued that process of that visual change that was going on. And really, the major change was happening where? It was happening in this blue region of the spectrum, right? So we see, yes, there's some change occurring in the green and some change occurring in the red, but the most dramatic change, the area where the greatest difference was occurring is right here in the blue region of the spectrum. Okay, so we could see this sheet going from here possibly to here, and then eventually to here, depending upon what the ultimate optical characteristic the customer wanted. So the Institute was able to gather this information off their GE recording spectrometer they had there. So then they sit down with the customer and said, okay, here's what we found. We found that this is the scenario that we have in the bleaching process. As we remove that lignin, as we remove that color from that, the sheet's getting lighter, but the greatest change is occurring here in this region of the spectrum. Okay? So with that information, they said, okay, how can we take this, because you guys can't put a big GE recording spectrophotometer in your lab. We've got to come up with a small analytical optical tool for evaluating this process. Well, if you were going to do that, where in this spectrum would you do that? Would you do that where the least amount of change was occurring or the greatest amount of change was occurring? Yeah, you want to do it over here where you had the greatest, not variation, but you had the greatest change occurring. So this is going to give you the ability to to really drill into and see, okay, what are the minor changes that are occurring in that process? And I do that where the greatest change is occurring over here in the blue region. So with that decision made, the Institute went to work on developing a very simple basic instrument that would look at the blue reflectance of a sample. Okay, how much blue light energy was it reflecting? Because really that's what they wanted to do, is measure just the blue region of the spectrum. Again, this is the 1930s, so that there wasn't as much technology and options as we have today. They used a copper sulfate filter. That was a commercially available filter at the time, and that is a very deep saturated blue color. Okay, so they used that, and they put that into an instrument that they had manufactured and put together. And what they did is they passed light through, focused it on the sample, focused that light here. That light would reflect energy, and then they would pass that light through this blue filter, and they would have a photocell sitting here, and it would capture that light energy. Okay, so with that being the scenario, as I'm moving through this bleaching cycle, I'm letting more and more blue light being reflected off this because I'm not absorbing that light any longer. And as that's the case, if I'm measuring just that blue light energy, that number is going to go up as I remove that yellowing or the lignin here, and I let more blue light come through. So they developed this instrument, they looked at it, and when they measured the spectral characteristics of this filter in this instrument, they found that the energy distribution of that filter looks something like that. And it ended down here around 395, ended over here about 505, and it had a peak wavelength at 457 nanometers. And you may hear that today. You may hear this number, 457, and that relates to the central wavelength, the dominant wavelength of this function that we have over here that measures this process here. Okay, so they did that. Now what they're doing is they've got an instrument that's looking at basically energy inside this area right here. Okay, and when they did that, they were able to put that in the instrument and look at that, and they came up with this term they called brightness. Because as they were looking at it, as that pulp was going through this process and they were getting this higher number, they said the sheet was getting brighter. So we came up with this thing called brightness based on this distribution right here. Think about this though. If you're measuring here, do you see the green or the red energy? No, you're not seeing that. Brightness is only looking at the sample's ability to reflect blue light. And so if we could come up with one basic definition of brightness, it is that. It is the ability of a sample to reflect blue light energy. And that defines brightness as we use it today.